Hello, welcome to Electrostatics. We're going to be covering a lot of electricity and magnetism in the upcoming weeks, and this is AP Physics C. Let's get started. Alright, so we have to start with fundamentals. So what is electric charge? Well, some materials can be electrically charged, and this is just like an observation that we made many years ago. And there's two types of charges, and they're arbitrarily named positive and negative charge. So we observed in nature that there's these two groups of charges, and we just assign the names at random, positive and negative. And in the positive group, we have protons that carry positive charges, and we say that electrons that carry a negative charge. And another observation that we made is that charges of the same type, they repel each other, and charges of opposite types attract each other. So these are just some fundamental properties that we've seen in nature. In an isolated system, electric charge is conserved. And in 1963 to 1953, Robert Millikan, he discovered that electric charge Q is quantized. And this is a very interesting observation. This means that, you might think of things like water, seemingly like sand, for example. It seems to be continuous. Like it seems that you can have an arbitrarily amount of sand, but if you look at it at a very microscopic level, you'll see that there's you have 1 grain of sand. So at any point in time, you can count the number of grains of sand you have. So it's quantized. It's not continuous. It's discrete. And the smallest amount of charge, the lowest denomination of charge, is our fundamental unit. So we say that electrons have a charge of negative E, whereas protons have a charge of plus E. So these are our two groups. All right, cool. Now, materials in general are either conductors or insulators. And what we've observed in nature is that a material will either allow charges to flow through it, and that means that they're a conductor, or they won't allow any charges to flow through it, in which case we call it an insulator. So if we were to send charges through a material, depending on what occurs, we could classify it as a conductor or insulator. And what we can do is we can charge materials through a process called induction. And this is something that we saw maybe in Physics 1. And you can see here that you have a conductor, and you have an equal amount of both positive and negative charges. So in total, the total charge is 0, but there are positive and negative charges. And what we'll do is we bring a rod over here that's negatively charged. And when we bring the rod over, well, negatives repel each other, right? So what will happen is that we'll get negative charges moving all the way to the right side of the cube, of the sphere. And as a result, we'll have positive charges going to the left side of the sphere, being attracted to the negative charge. And then what we'll do is we'll attach a wire to the sphere, and we'll attach it to the ground. Now the ground is just like this, big source of positive and negative charges. And what will happen is that, well, because there's a lot of negative charges in this area, and if there's a lot of negative charges, that area wants to kind of be neutral. What will happen is that the excess negative charges will go into the ground. So what happens is that in this area now, in this right part of the sphere, it's pretty much evenly distributed over here. And then what we'll do is we'll just simply remove the rod, and all the charges will equally disperse. And remember, because some negative charges left the sphere in this step over here, the resulting sphere has now an excess amount of positive charges. So this is a way where we can take a material that was once neutral, and by not even touching the material, just by introducing a charged material next to it, we can cause the material, grounding it, we can cause the material to be charged as we wish. And this process is called induction. Okay, now we're going to get into some equations. So, we made some observations in nature, and now we're going to look at actual equations that we see um, that kind of govern the movement of charges. So, a point charge refers to a charged particle of zero size, very similar to point mass that we did in mechanics. And what we can do is, if we remember in mechanics, we had a notion of force, right? F equals ma. There's a such thing as called an electric force, and we use Coulombs Law. So Coulombs Law provides the magnitude of the electrostatic force between 2 point particles. Now remember, two like charges and two positive charges and two negative charges, they'll repel versus opposites which attract. So the Coulombs Law states that the force between two particles, the magnitude of the force, is k sub e q1 q2 divided by r squared. Now k sub e is a constant, r is the separation distance, and q1 and q2 are the charges of the point particle. Now I want you to think for a second is that when we were in mechanics, we were looking at, objects that have a certain mass associated with them. Now in this world here, we're assuming that all objects are, they're zero size, they don't have any mass. That's our running assumption. We're more interested now in the charge of that particle. So we're not looking at mass, but we're looking at the charge. But those two are very, you can draw parallels between the two. So this is Coulomb's law. And k sub e is a constant which equals 8.89 times 10 to the 9th Newton meter squared per Coulomb squared. Now some clarifications. So point particles, they do actually have mass, but they have zero size. This is kind of our assumption. So what we care about, though, is that the charge associated with them. So we're not going to look at any type of forces like, due to gravity or anything. We're only going to be caring right now about forces relating to the charge. So Coulomb's law gives us the magnitude, right? But it's up to us to figure out the direction of that force. So if you have two positive charges, we'll know that the force is going to point outwards because they're going to repel. And if it's positive and negative, we know that they're going to be attracted. And force is measured in newtons. All right, let's start with an example. So we have two identical small charged spheres, each having mass m, and they hang in equilibrium. Okay, so we have two charged spheres having mass m. So in this problem, we're actually going to be mixing both the world of charged particles. So in Coulomb's law, we're looking at charged particles. We're going to be mixing that as well as what we learned in mechanics. So here in this problem, we're actually going to care about mass as well. So here we have a string of length L. So this is of length L, and it makes an angle theta with the vertical. What is the magnitude of the charge on each sphere? Now, if you think about this like intuitively, suppose that these weren't charged at all, what would happen? Well, it would kind of just, hang like this over here, right? But because, they're both charged, they're repelling each other, there's going to be a force, of repulsion. And we can find that using Coulomb's law. And why don't they just keep repelling each other and going, all the way out to infinity? Well, it's because, you have this wire, you have this string over here that's preventing that from happening. In fact, I would argue that the tension in the string is preventing the masses from going infinitely far in both directions. So that's kind of like the gist of what we're going to do here. Now, so the first step, of course, is, label all the forces. So here we have in green, we have the electrostatic force. In purple, we have gravity. And in red, we have the tension of the string. And notice that the tension of the string the sine of theta, which is, this horizontal component here, is going to be the part that has to balance out the electrostatic force. So we're going to be interested in this equation here, Ft sine theta, which gives us this component here, and needs to be equaling this component here for it to be in equilibrium. Well, that's one equation. The other equation is simply, the vertical component must balance out with gravity. This way, the sum of all of our forces is 0. So we end up getting these two equations, electrostatic and the x component of tension, and gravity and the y component of tension. And we can, either solve for t and substitute into this equation, or we can just divide both equations, and we end up getting tangent of theta equals Fe divided by mg. So Fe equals mg times tan theta. Now, what is tangent of theta? Also we have to note that the sine of theta, so theta is up over here, is equal to opposite, which is A divided by L, right? So our magnitude Q, which is equal to the square root of this mess over here, and we substitute it in, so we end up getting, and this equation, by the way, comes from F sub E equals Q, K sub E Q over R squared, right? Sorry, I'm skipping a few steps in the solution here. This equation over here is coming from the fact that F sub E equals Q1 Q2 over R squared times K sub E. And Q's, they're both identically charged because these are two identically small charged spheres. So we can just say that Q is equal to the square root of this here, so basically this equation here. And when we substitute it in, we see that we just solve for Fe, and we know what R squared is. R squared is this distance of separation, which is just 2 times A, and we end up getting this expression as the magnitude of the charge on each sphere. Okay, now when we talk about gravity as a force, we were saying that F equals mg. So here g is a constant, and m is the parameter that varies between different objects. So we kind of had g as a constant. Now the problem is that we want a way to describe electric forces without reliance on the charge. Right now we're saying that if you have a 2-charge system, so if you have a charge over here and you have a charge over here, well, every time we apply Coulombs law, we're doing F equals K sub E times Q1 times Q2 divided by R squared. We always have a dependency on both masses. And what we want to do is, just to make things simpler, we want to avoid having dependency on the mass that we're on the particle that we're kind of placing around on our test charge. So what we're going to do is we're going to have this notion of an electric field. So for a source object, and this over here is our source object, we say that there's an electric field that exists around this object. And the electric field is just saying that, at this point over here, this is the value of the electric force. At this point over here, this is the value of the electric force. And it's just saying at each point, with respect to that source charge, what is the value of the electric force? And to calculate it at a specific point, we're going to place a test charge in some area. And the electric field acting on the positive test charge is defined as the electric force at that point divided by the test charge. So in other words, we're going to have a source object here, SOURC. We're going to have a source object over here, and we're going to have a test charge here. And what we're going to do is we're going to measure what is the electric force over here. Let's just say it's like F. And then we're going to say that the field here, E, at this point, is equal to F divided by the charge. And we're going to do this at every single point. So we're going to have a point here, 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 here. And we're going to call this whole thing a field. So now at any given point, if I put a new particle with a specified charge, to figure out the force, all I have to do is I have to take, to figure out the force, all I have to do is I have to take the charge on that particle and multiply it by the electric field value at that point. Okay, so we just went over this point here, and just a few things. So electric field is a vector quantity, of course, because if you're a positive versus a negative charge, that matters on like where your force is going to be. Are you going to be attracted to the source, or are you going to be repelled from the source? So it is a vector quantity, and the unit is newtons per coulomb. And this makes sense, right? Because newtons is force, and per coulomb we were dividing by the test charge. And the electric field always exists if there's a source charge. The test charges are a way of measuring the strength of the electric field at a point. So we're just putting a test charge just to measure it, and then we're going to divide by that value. And if we get another value that's twice as big, we're going to remultiply it. So it's just kind of our test mechanism. And what we're going to do later in this PowerPoint is we're going to actually use calculus to compute the field strength at any given point. Okay, so some more intuition, just because this is a very I think this is a very confusing topic. So you can think of also as electric field as a topographic map, and it helps us assess the strength of the electrostatic force at various points around the source charge. So imagine a field, and if you put a positive source charge, if you introduce a positive charge, this is kind of like your test charge, the force is going to be in the same direction as the field. And what we're going to do is we're going to be drawing this out like with arrows and everything, and it'll make sense. This is kind of like what it looks like. We'll get to it in a second, but it'll make sense in a minute. So if we introduce a positive charge, the force is going to be in the same direction as the field. And if it's a negative charge, it's just going to be the same magnitude but opposite direction. And it's kind of similar to gravitational fields. Once we know the mass, we can then calculate the force due to gravity, F equals mg. But for gravity, it's constant everywhere on Earth, on the surface of the Earth. Your gravitation, your g is the same. It doesn't change. But in E&M, your distance, your separation from the source charge, how far you are away, that matters. That has an effect. And that's why we have to introduce this, because electric fields, they vary with position. Okay, now one more thing. So suppose our source is now 3-point charges. Now the electric field is just going to be the sum of each of those 3 electric fields. It's additive. So at each point in space now, if we have a test charge, it's going to experience the forces due to all 3 source charges. So if you have source charge 1, source charge 2, source charge 3, and this is our test charge, it's going to experience 3 different forces at each point from each of those particles. So it'll just be the additive sum of the 3 electric fields. All right, just few pictures. So if Q, so we have two particles here. We have a positive one, and we have a test charge here. Now, if Q, our test charge, or our source charge here is positive, then the force on the test charge, Q0, is directed away from Q. So what this is saying is that if our source charge here is positive, then our electric field lines are going to point outwards. Now, same thing over here. You know, this is the same setup here. So our source charge is positive. Our electric field line is going to point outwards. So our force and our electric field are both, you know, in the same direction. Same thing over here. So if our source charge is negative, if Q is negative, then this means that our test charge is, you know, going to be attracted, because we usually assume that test charges are positive. It's going to be attracted, our force is going to point inwards, and we copy that notation when we do electric fields, so our electric field is going to point inward. Okay, so just memorize this. For positive point charge, the electric fields go out. For negative, they go in. Positive out, negative in. Now, these pictures are kind of important because they do appear on the AP exam a lot, and there's some rules that kind of we wrote down to help you come up with these diagrams. So there's three things. One is the direction of the line, the amount of lines, and like the spacing or like the density of the lines. So the direction of the lines. If the source is positive, the lines go out, and if it's negative, the field lines go in. That's an embarrassing typo. The amount of lines. So if there's a lot of lines, you're gonna assume that the source has higher charge in magnitude. So you can see here as an example that positive 10Q and negative 10Q, remember Q is our it's our like a charge of like 1. So this would be a charge of plus 10, this would be a charge of minus 10. It's our discrete multiplier. So they should both have an equal number of field lines because they're equal in magnitude. But minus 10Q should have more field lines than 3Q because it's higher in magnitude. 10 is greater than 3. So you should have more number of field lines. Now for spacing, the density indicates a relative strength. So if there's a lot of lines that are close to each other, that region has, the electric field in that region is very strong. And one word of caution, you should never have two field lines cross. And this is because if you have two field lines that cross, say it looks like this over here, this means that at this point where they cross, the particle is experiencing two forces here, which doesn't make sense. If you have one source, then there should only be one corresponding force at that point. So you should never have two field lines crossing here. Even if you have multiple charges at every given point, the particle should only experience one force. So you should superimpose both fields if that's the case. So if you're only drawing like one electric field, and then you say that electric field is, due to the configuration of the system, you should superimpose all of the electric fields, and as a result, there wouldn't be any field lines that cross. These are some examples here. So you can see in this case, you have two positive charges, right? And the field lines go out. So looking at our rules, positive source, field lines go out. The number, well, this is plus one. There should be equal number of lines coming out. Also, the spacing should be relatively the same. Like if you're over here versus over here, the spacing indicates the strength. So here and here, you have the same strength due to symmetry. same thing over here and over here. In the center over here, what would you experience? Well, you would experience like repulsion, right, from both of these positive charges. So yeah. Now let's look at this point, this diagram in the center. So in this case here, we have positive and negative. The number of field lines coming out of both should be equal. And look now in the center over here. In the first diagram, we could not have any field lines in this area here, right? Because otherwise the lines will cross. Now, over here in this diagram here, you can see that the fields are kind of married to each other. And this is because if you're a test charge and you're in the center, here you'll be directed towards, remember test charges are positive, you'll be directed towards this negative charge. You'll be repelled away from the positive charge. Versus here, well, you're kind of going to go crazy. You're going to be repelling, you'll be repelled outwards. You'll be going out like this here or out this way over here. So in fact, in this area here, it's going to be super different than it is going to be over here. Now in this third diagram, you have plus 2q and minus q. So what we'll do is, if you count the number of field lines, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And here you have 1, 2, 3, 4, 5, 6, 7, 8. So you have 16 on the plus 2 and you have 8 on the minus q. That checks out, right? Because this charge here is 2 times as strong as this one. The field lines look right. For the positive charge, they all go outwards. For the negative, they go inwards. And finally, the spacing makes sense. It's going to be, your field is going to be stronger here. You have a greater force. And if you're out over here, you don't have as much of a force. You really feel the force when you're between these two charges because you have both the attraction and you have the repulsion. Okay, so special cases. So suppose we place a charged particle in a uniform electric field. What is the resulting motion? So a charged particle in a uniform field will have a constant electrostatic force. And this is very similar to gravity, right? So we were saying earlier that on the surface of the Earth, G is the same. It does not vary with position. So you can kind of think of a constant uniform field as being similar to the mechanics that we've done with gravity. All right, so now we have some easy derivations. Okay, so what we want to do now is, earlier we were looking at point charges. We were saying we have 2 points here. What is the force between the two? Now we're going to look at the electric field for non-point charges. So over here we have, this big mass of basically electric charge, and we're interested in a specific point P. What is the electric field at that point? And all we're going to do is we're going to treat this mass as a series of small charges, and we're going to sum up the electric fields due to all of those charges, and that's going to be our answer. So how do we sum up something continuous? Well, we use an integral. So this is what we're going to do. K sub e, q over r squared, but this time we're going to do dq, a small point, and we're going to integrate. Now, there's a few types of problems that we're going to see. So there's 3 main types. Volume, so this is like 3D charge densities. Surface, this is like a 2D charge density, like a sheet. Or 1D, which is the best example because it's a lot easier. And this is just one-dimensional along a line, like along the x-axis. So just think 3D, 2D, and 1D. And the thing that we're going to just keep on coming back to, we did this earlier, is looking at densities. So in the 3D case here, we're going to look at rho, which is equal to the charge per volume. So this is charge per volume. And the differential form is just saying that a little bit of charge is equal to our charge density times a little bit of volume. Now for 2D, it's very similar. So we say sigma, this is just the variable that we use in the 2D case, is equal to the charge of the sheet divided by the area of the sheet. So this is for a constant charge density. And in differential form, it's just that a little bit of charge is equal to our density times a little bit of area. And for the linear case, it's very similar. It's our charge per unit length. So charge divided by the length gives you our charge per unit length. And our dq, a little bit of charge, is equal to our density, charge per length, times a little bit of length here. So it's important that you look at the problem, you classify it, is it 2D, 3D, or 1D, and then you write down immediately which one of these equations that you have to use. So in this problem here, I'm not even going to read it. I look at it, I see an x-axis, it's 1D. We're going to look over here, we're going to be using this equation somehow. All right, let's read it. So a rod of length L has uniform positive charge per unit length lambda. So they're already giving us this parameter here. And total charge Q. So all I'm going to do is I'm going to write down lambda, which equals Q divided by L, right? So I just copied down this equation here. And we're given this here, we're given this here, and we're given this here. So they're just kind of telling us everything. Now calculate the electric field at a point P that is located over here, at a distance A away from the other end. Okay, so calculate the electric field at point P over here. Now this is kind of like a classic problem where we're just going to use the formula that we wrote down. So this is P, our rod is over here. And all we're going to do is that if we want the electric field, all we're going to do is we're going to say that suppose we take a little bit of charge over here and we look at the electric field. And we do that for all these points on the rod. So we take next this little mass over here and we take the electric field. And we do the same thing for all of these points on the rod and we sum them all up. And that's going to be our answer. So we're going to take a little bit of charge, we're going to look at the field due to that charge, and we're going to do the same thing again, just to shift it over a little bit, and we're going to do the same thing until we've covered the entire rod. So yeah, the trick is to sum up a bunch of charges. Okay, so just remember K sub E, Q over R squared. In this case here, K sub E dq, we're going to take a little bit of charge over here. Actually, we can just follow the diagram. We're going to take a little bit of charge over here, and we're going to divide it by the length. So how far away are we? Well, if this is our distance away, if we call x our distance away, it would just be x squared. And yeah, so what we're going to do now is we're going to now set the limits of our integral. So we're going to be integrating from x equal to a, which is this point here, all the way up to x equals a plus L. And all we're saying is that we're just specifying like where our charge is. So our limit is going to say, our limits of our integral is going to be from a to L plus a. And if we solve this integral, we can take out K sub E because it's constant. We can take out lambda because it's constant. So we end up integrating this over here, whose integral is this, and then we plug it in, and we end up getting this over here. Okay, now we're going to be skipping this here, this uniformly charged disk, but I'll skip through it very quickly, just in case someone wants to pause and read. Now, we're going to look at electric potential next. So, just now, we were dealing with electrostatic force, and now we want an analog to energy. So, if you remember in mechanics, we had force, and then we had a chapter on energy, which was a completely different topic, and we had another topic called momentum. We've just finished the electrostatic force chapter. Now we're going to look at energy. And the observation is that it requires work to move a charge. Now, the electrostatic force is conservative, so only the start and the end points matter. If a charge is free to move, it will do so in response to the electric field. So if you have a source charge and now you introduce a new charge, well, that new charge is going to experience a force and it's going to move. Now, when a charge is displaced from point A to point B, we're going to say that the change in electric potential of the system is given by this equation here. And all this is saying is that the energy required to move a charge from point A to point B is minus Q, minus a charge, times the integral from point A to point B of the electric field dotted with the displacement vector. If you think for a second, like if you say like you have, let's say we have an electric field that looks like this here, and we move a charge from point A to point B, and we say that suppose the charge is positive, then do we expect there to be for it to be positive or negative energy? Well, the charge itself will follow the electric field line, so actually it'll be negative, right? Because you have minus Q, which is going to be negative, times E, which will be positive because we're moving in the direction. So we're going to end up getting a negative number, which makes sense because it's going to, the system wants to move in that direction. We're not going to be putting any energy into the system. Now, there's a problem here. When we were looking at this, it was all dependent on this test charge again. So just like in electric fields, we wanted to get rid of the dependency on the particle that we added in. The same thing in this case. So we don't want the dependency on Q. So what we're going to do is we're going to define voltage, which is the potential difference between 2 points. And all it is the potential energy, the electric potential divided by Q. And when we say voltage, all we're saying is that we have 2 points over here, and we're going to say, what is the change in energy from these 2 points here? And just remember, like, voltage is defined as like the difference between 2 points. And yeah, remember in gravitational potential, we were looking at, only the relative change between 2 points. If you're up on a hill versus you're at the bottom, we're only looking at the potential between those 2 points. It's very similar here. Now, there's a few things to keep in mind. The potential energy and electric potential are different. So potential energy is the system level energy. So you have like a configuration and you sum up what is the potential energy of the system. Now the electric potential, it only depends on the source charge distribution. So you look at a source charge and you have a electric potential due to that source charge. So if an external agent moves a charge into a field, the amount of work done is then the charge times the voltage, the potential difference from point A to point B. This is a little confusing, so I'm just going to kind of say it one more time. When we're talking about electric potential, we're saying we're moving a charge from point A to point B, and this requires work. And voltage is just a way of being lazy and saying that, well, we don't want to keep expressing things in terms of, whatever charge you give us. So we're just going to say, we're going to say 10, and then we'll say that the electric potential is 10 times whatever charge you give us. So the voltage is 10 volts. If you give us a particle of, say 10 coulombs, well, then the energy will be 1 volt times 10 coulombs, for example. So it's just a way of expressing something without having dependency on the actual charge itself. Units wise, 1 volt is 1 joule per coulomb. This makes sense. Joule is energy. Per coulomb, we've divided out the charge. Now, in a uniform field, very specific case now, we're saying that, that we have a uniform field. The potential difference between 2 points in a uniform electric field is just minus the electric field times D. Now, note that E is constant because it is an electric field, a uniform electric field, and D is the distance away. The change in potential energy is just Q times the voltage. So it's Q times the voltage that we just wrote down. And remember that electric field always points you to lower potential. So moving in the direction of the electric field moves it to a lower potential. And in this diagram here, you can see that point B is at a lower potential than A. Think of it kind of like a slide. Like all of these arrows are kind of like a slide. And you move from point A to point B, you're kind of going down the slide. So you're at a lower potential. Now, from A to B, you're going to a lower potential. Now, for B and C, these are both at the same electric potential. Now we want to actually calculate what is this electric potential. Well, we can use K sub E times Q divided by R as our equation for voltage, and we're going to skip the derivation. And one thing just to be clear is that voltage is the potential difference between 2 points. So it's customary to pick V equal to 0 at a distance infinitely far away. So your voltage is kind of like how much energy per charge it takes to move that charge from an infinite distance away all the way up to a distance from your source charge. So the potential energy then is K sub E Q1 Q2 over R. And note that if the charges are the same sign, this is positive, and if they're different signs, then it's negative. Now for multiple charges, you can apply superposition. So this is saying that if you have multiple charges, you take the potential for each pair of particles. Okay, so we'll do a few more clarifications. Imagine placing a source charge in space. Okay, now there's two things that will occur. One is that this charge sets up an electric field. And this is related to the electric force. The other thing is that the charge sets up a scalar potential, which is related to the electric potential. And the reason why electric fields and scalar potentials is that we want a way to analyze independent of this test charge. And the relationship between electric field and voltage is this equation here. And one thing you can just see is that you can see that here we had U equals K sub E Q1 Q2 over R. If you take minus the, if you look over here, energy electric field is minus the derivative of voltage, right? If you look at voltage here and you take the derivative, you end up getting the K sub E Q over R, right? So here you would take out a Q because it's voltage, and then you would take the derivative and you get minus K sub E Q over R squared that we're used to from Coulombs Law. Okay, so now pause the video if you're watching this recorded. The next topic is Gauss's law. So for Gauss's law, we were discussing electric fields, and then electric fields help us understand forces, right? So now we need to kind of be more rigorous in the way that we look at electric fields. And we were drawing diagrams earlier, but now we're kind of interested in relationships between how we draw those lines and the charges itself. And remember that we said that the number of lines is proportional to the strength of the field. So we had a charge of Q, and then we had a charge of 10Q, and the 10Q had 10 times more field lines emanating from it than the single Q. Now, one concept that we'll see now and also in magnetism is flux. Now, you can think of this as, imagine in this diagram here you have a bunch of field lines. And now imagine you hold like a piece of paper at some oblique angle like this over here. Now consider the other case. Now consider you hold up the paper completely vertically over here. You hold it vertically. And also consider a case where you hold a piece of paper horizontally. Now there's going to be different impacts, right? So if you hold it vertically, perpendicular to the field lines, you're going to capture all the field lines onto your paper. If you hold it horizontally, you can kind of think that you're not really capturing anything actually. They're just kind of moving parallel to your surface. And if you do it at some oblique angle, well, you're going to be capturing them to a certain degree, right? You could argue that as you move more and more vertical, you're going to be capturing more and more strength of the field lines. They're going to pass through you, but they're not going to be passing perpendicular unless you're actually perpendicular. So as a rough thinking, this is kind of what flux is. It's a measure of how much you're capturing. And the way that we look at flux is we look at this formula here, E sub E, which is the electric field, times A, which is the area of your surface, times cosine of theta. Now this theta here is basically the result of a dot product. So if you're and this is the dot product with respect to a normal to the surface. So a good way of thinking about this is that if the normal to your surface, and in the normal is literally, normal line is kind of like a perpendicular in 3D, you can imagine that. So if your normal vector, here is completely parallel to your electric field, so this is the case where your electric field lines are going this way and your surface is perpendicular. That means that your normal is also going to be in the same direction of your E field, and the cosine of that angle is going to be 0, right? Well, the theta is going to be 0, the angle between those two is 0, so the cosine is going to be 1. So that means you have full kind of capture. And if your surface here is parallel to the field lines, then your normal line and your field lines meet at 90 degrees, and the cosine of 90 is 0, so you end up getting 0 flux. So your theta is defined to be the angle between the normal to your surface and the electric field lines. So just remember, normal to the surface and electric field lines. And this is theta, which is your flux, capital theta, and our electric flux is going to be a surface integral, so we're going to be summing up over the entire surface and of your electric field at each point in the surface times that small section of the surface. And what we're going to look at actually is we're going to be thinking about closed surfaces. So in this picture here, we kind of just have a sheet, right? But we're going to look at, imagine a spherical surface. It's closed, and we're going to be thinking about, well, what's the net number of lines that are entering. So the net is actually leaving minus entering. That gives us our total number. And if it's positive or negative, that means that we have more lines leaving than entering, or we would have more lines entering than leaving. And if you think about it, that probably means that we have a charge inside. So So Gauss's law is essentially that. It's saying that there's a special property when we calculate flux over a closed surface. And it says that the net flux through any closed surface surrounding a point charge Q is given by Q divided by epsilon 0. So Gauss's law is saying that the electric flux is equal to the enclosed charge divided by epsilon 0. So if there's no charge inside, then the flux of that closed surface should be 0. And the sign of the flux is given by the dot product, of course. And yeah, we went over that the area vector, the normal vector, is perpendicular to the plane of the surface and directed outwards. And a few reminders, this is just off to the side, we might use this in the next problem, is that suppose we have a function of known charge density, we can find the total charge by integrating. So this is saying that this is just saying that we can integrate our density, our volumetric density. We can keep integrating and stacking on more layers in order to get the total volume of something. And we can do the same thing in 1D and 2D. So in 2 dimensions, if we have a sheet, well, we can integrate, integrate lines basically that make up the sheet. And if we have a 3D object, we can integrate like shells, and that would in aggregate be the entire 3D surface. And remember from the very beginning slides that we had certain materials and would run charges through them, and we noticed that for some class of materials, which we call insulators, we wouldn't be able to pass charge through, but for conductors we were able to. So for insulators, they hold charge everywhere, and for conductors, what we see is that they only hold charge on the surface. Now, the key fact for Gauss's law is that the shape of the surface does not matter. We want to construct shapes that are highly symmetric, and this is because in Gauss's law, we have this. And if we have symmetric shapes, like where the electric field lines are the same everywhere, we can pull the E out of the integral. And we also want, either parallel or perpendicular. And this is because then the dot product, we can pull out, we can drop the cosine theta. It would evaluate to 0 or 1 if we're able to exploit this. So now we're going to look at an example. So an insulating solid sphere of radius A has a uniform volume charge density rho and carries a total positive charge capital Q. Find the magnitude of the electric field at a point outside the sphere. So an insulating sphere has a radius of A and a uniform charge density rho. So just keep that in mind. Uniform charge density rho, and we have the total positive charge Q. So if we have the total charge and we have a volume charge density, then we can figure out the volume, right? I won't scroll up, but we had the relationship, like density equals charge divided by volume. Okay, so what we're going to do is we want to find a Gaussian surface. So the first step is we're going to figure out what our surface is. And this comes with practice, but a good choice in this case is a sphere that surrounds this initial sphere. And the reason why is that at every point on this outer sphere, the electric field is going to be the exact same. And this is just due to symmetry. If you rotate the sphere a little bit, it's the same configuration. That's how you can argue with symmetry. And because of this, and because of the fact that the electric field lines are actually going to be going straight out, the normal vector with the surface and the electric field lines are both parallel. So theta equals 0, cosine theta equals 1. So we can drop this dot product and we just have E times dA. So we can calculate our flux we get the integral of E dot dA, which is just E dA, and from Gauss's law, that's equal to the Q enclosed, which is capital Q given to us in the problem, divided by epsilon 0. But the trick is that the electric field is the same everywhere, so we can actually pull it out of the integral. So E dA is just E integral dA, and the surface area of this here is 4 pi r squared. That's the surface area of a sphere. So we get E times 4 pi r squared is equal to Q divided by epsilon 0, and solving for E, we get this expression over here. And this holds, of course, when we're outside the sphere. Now we're going to find the magnitude of the electric field at a point now inside this sphere. Now remember, for insulators, the charge is kind of evenly distributed around. If you look at if you take a device physics course, or if you take a solid state course, you'll learn that the charges are kind of fixed in place. So now we're going to be taking a sphere that's inside the surface. And the only thing that's changed is that the electric field, by the way, is still the electric field is pointing out and our normal vector is pointing out. So we still have the trick of saying cosine of 0 is 1, so we can drop the dot product, and we can also pull the E out of the integral because it's going to be the same everywhere on the surface. But the only thing that's changed is that the enclosed charge is now going to be less. In fact, the enclosed charge now is going to be our volumetric charge density, charge per volume, times the enclosed volume, which is 4/3 pi little r cubed. So this is our new Q enclosed. And now, if you just substitute this in, if you keep everything else the same, we still have 4 pi r cubed as our surface area. We end up getting this expression here. And then we can substitute a little further. We know that rho is equal to Q divided by 4/3 pi times a cubed. This is our total charge divided by the total volume, and substituting that in, we get this expression here, and that ends up becoming K sub E Q divided by a cubed times r. Now, one thing that we did over here is we plotted on the x-axis how far away you are from the center, and on the y-axis we plotted the electric field strength. And in this first regime, when you're inside the sphere, you notice that your electric field goes up and up and up and up. Like if you're here, it's becoming higher and higher and higher. And once you reach the surface of the sphere and start to move outwards, then it starts to drop off. And now, as a last example, which we're not going to go over here, is the long infinite line of charge. So in this problem here, we have an electric field at a distance r from a line of positive charge of infinite length, and we have a constant charge per unit length lambda. So here we have a one-dimensional problem because we have a line of charge. And I wrote down an explanation, but at a high level, our Gaussian surface is going to be something where the electric field is the same at every point, and something where we have a dot product that we can either remove or it's equal to 0. And in this case here, without getting into too much details, we're going to choose a cylindrical surface. And the reason why is that at every point on the outside of the cylinder here, the electric field is going to be the same because of symmetry. It's like this point here and this point here. If you were to just rotate the cylinder the configuration is still the same. You have the same electric charge. And this caps here, and remember we have to choose a closed surface. So we do have to we have to have the top and the bottom part of the cylinder. Well, these parts don't really matter as much because the field lines are gonna be going parallel to it. So actually, no field lines are gonna pass through the caps. So electric field there is gonna be 0. So we're only gonna have fields on this surface here. And yeah, without getting into too many details, like this is what we end up getting, and we end up using the same substitution. So yeah, so we're just slightly above 1 hour. Thank you all for coming, and we'll be back next week with some more videos.